Imagine asking a simple question: what's the fastest thing in the universe? You already know the answer, don't you? Light. That's what we learned in school, what we've been told since childhood. Photons racing through the void at 299,792,458 meters per second, the cosmic speed limit, the ultimate velocity beyond which nothing can travel. It's a comfortable certainty, one of those fundamental truths we can lean on when the universe gets strange. And yet, what if I told you that right now, as you listen to this, there are objects in our universe moving away from us at 5 times the speed of light? 10 times? 100 times? Not because they're breaking Einstein's laws, not because relativity has been disproven, but because the fastest thing in the universe isn't a thing at all. Hello, and welcome to the Sleepy Astronomer. Tonight, we're going to walk up to one of the cosmos's most rigid rules, that nothing can exceed the speed of light, and watch it bend in a way that still respects physics. We'll catalogue the universe's speed demons, from our fastest spacecraft to hypervelocity stars flung from galactic cores at thousands of kilometers per second. We'll watch particles approach the cosmic speed limit, and then we'll discover what's really racing, because there's something out there, something happening right now in every direction we look, that makes all these velocities look like they're standing still, and understanding it changes how we see the night sky forever. If you're settling in for the first time, welcome to these gentle explorations of cosmic mysteries. And if you've drifted with me before through deep time and distant stars, it's wonderful to have you back for another journey. If these peaceful wanderings through space and time bring you comfort or curiosity, don't forget to subscribe so you don't miss the next journey into the cosmos. And if this paradox intrigues you, what could possibly be faster than light without breaking the universe's rules? A gentle like helps others find their way to these nocturnal wonderings about speed, distance, and the nature of space itself. Here's what makes this story so compelling. Humans have always been fascinated by speed. Ancient Greeks imagined Hermes, the messenger god, moving swifter than thought itself, carrying messages between realms faster than mortals could perceive. We've built myths around impossible journeys, cosmic strides that span creation in 3 steps, bridges that shimmer between worlds. Speed has always represented power, mastery, the ability to transcend limitations. And in modern physics, we found what seemed like the ultimate expression of that: the speed of light, a boundary written into the fabric of reality. Einstein showed us why nothing with mass can reach that speed. And as objects accelerate, they gain not just velocity but relativistic mass, requiring exponentially more energy to push faster. By the time you approach light speed, you'd need infinite energy to accelerate even slightly more. It's an elegant, impassable wall. The cosmic speed limit isn't arbitrary, it's architectural. The universe is built around it. So, take a deep breath. Let your mind settle into the quiet around you, and get comfortable. Because what if the fastest thing in space isn't travelling at all? Before we can understand what's really racing through the cosmos, we should probably establish what we mean when we say something is fast, which sounds obvious. You know what fast means. You've been fast, you've seen fast things. But speed turns out to be more slippery than it appears. And I promise this will be more straightforward than relativity makes it sound, though admittedly, relativity does like to complicate things. Speed, at its most basic, is just distance divided by time. How far something travels in a given period. Meters per second, miles per hour, parsecs per year, if you're feeling particularly astronomical about it. Simple arithmetic. The sort of thing you learned before you learned that the universe has opinions about reference frames. But here's the thing that makes speed interesting. It's always relative, always measured against something else. When you say a car is moving at 100 kilometers per hour, you mean relative to the road, which is attached to Earth, which is rotating and orbiting the Sun, which is orbiting the galactic center, which is moving through the local group of galaxies. There's no cosmic speedometer reading out your true velocity because there is no such thing. Speed only makes sense when you specify what you're measuring it against. This might seem like philosophical hair-splitting, but it's actually crucial for understanding what comes later. Because when we talk about the fastest thing, we're inherently asking, fastest relative to what? Fastest through what? And those prepositions matter more than you'd expect. For now, though, let's stick with the intuitive version of speed. Things moving through space, measured against other things that seem stationary. Let's catalogue what humanity, and the universe itself, considers fast. We'll start with what we've built. The fastest things humans have ever created are spacecraft, which makes sense. When you're trying to explore a solar system where distances are measured in astronomical units and travel time is measured in years, you need to move as fast as physics and engineering will allow. Our current record holder is the Parker Solar Probe, a spacecraft about the size of a small car that's currently diving repeatedly through the Sun's outer atmosphere in an orbit that can only be described as ambitious. At its closest approach to the Sun, and by closest I mean skimming through the corona, the Sun's outer atmosphere, where temperatures reach millions of degrees, the Parker Solar Probe reaches speeds of about 191 kilometers per second. That's roughly 690,000 kilometers per hour. Fast enough to travel from New York to Tokyo in less than a minute. Fast enough to circle Earth's equator in about 3.5 minutes. Fast enough that if you could somehow drive it on a highway, you'd receive a speeding ticket that might actually cause the speed camera to file a complaint. This is genuinely impressively fast by human standards. The probe achieves these speeds through a combination of powerful rockets and gravitational assists from Venus, essentially falling toward the Sun in a carefully calculated trajectory that trades altitude for velocity. It's the fastest thing we've ever built, and it took decades of engineering and millions of dollars to achieve. For comparison, the Voyager probes, those intrepid explorers launched in 1977 that are now coasting through interstellar space, still sending back data after nearly 50 years, travel at about 17 kilometers per second. Still extraordinarily fast. Still fast enough to cross the United States in about 4 minutes. But compared to Parker, they're practically sauntering through the cosmos. Both of these speeds are impressive. Both represent the pinnacle of human spaceflight engineering. Both are, by terrestrial standards, almost incomprehensibly fast. And both are, by cosmic standards, embarrassingly slow. The speed of light, that cosmic speed limit we keep mentioning, is 299,792 kilometers per second. Let's call it 300,000 kilometers per second for simplicity, because those extra 208 kilometers don't matter much when we're talking about speeds this absurd. The Parker Solar Probe, at its absolute fastest, reaches about 191 kilometers per second, which means it's travelling at roughly 0.06% the speed of light. Not 6%. 0.06%. If light speed were a 100-meter dash, the Parker Solar Probe would be moving at about 6 centimeters per second. You could crawl faster. This is the humbling reality of cosmic speed. Our fastest spacecraft, the culmination of our best engineering, designed specifically to go as fast as physically possible, is still crawling by the universe's standards. It's like being very proud of your sprint time and then discovering you're competing against a fighter jet. But nature, of course, does better. Cosmic rays, high-energy particles that slam into Earth's atmosphere from space, regularly achieve speeds that make our spacecraft look like they're standing still. These are mostly protons, sometimes heavier atomic nuclei, accelerated by supernova shockwaves or the magnetic chaos around black holes or other violent cosmic processes we're still working to understand. They race through the galaxy at velocities that approach but never quite reach the speed of light. The fastest cosmic rays we've detected travel at 99.9999991% the speed of light. That's 11 nines. At this velocity, a cosmic ray crosses the distance from Earth to the Moon in about 1.3 seconds. It crosses the diameter of Earth in about 0.04 seconds, 40 milliseconds faster than you can blink. These particles are moving so close to light speed that the difference is almost academic. At these speeds, relativity starts doing genuinely strange things. Time dilation becomes extreme. A cosmic ray moving this fast experiences time roughly 70,000 times slower than we do. If it could somehow maintain consciousness, it can't. It's a proton. But humour me, a journey that takes 1,000 years from our perspective would feel like about 5 days from its perspective. Space itself contracts along its direction of motion. The galaxy, from the cosmic ray's point of view, is compressed to a tiny fraction of its normal size. This is relativity's way of enforcing the speed limit. As particles approach light speed, they experience reality differently. Time slows, space contracts, and crucially, their effective mass increases, meaning it would require more and more energy to accelerate them even slightly faster. By the time you're at 99.9999991% of light speed, you're asymptotically approaching an impassable barrier. You can get closer, add more nines, but you can never quite reach 100%. Not if you have mass, not unless you're willing to invest infinite energy, which even the most violent cosmic processes can't provide. So cosmic rays, for all their absurd velocity, still aren't the fastest. They're close, tantalizingly close, but they're still losing the race. The actual winner, at least the winner we've known about since 1905, is light itself. Photons, the particles of light, travel at exactly the speed of light. This is a tautology, obviously. Light moves at light speed, but it's worth stating clearly because photons achieve what cosmic rays cannot. They reach the speed limit, not approximately, not to 11 decimal places, exactly. 300,000 kilometers per second measured in any reference frame, under any circumstances. This is one of the strange, non-negotiable facts about the universe. The speed of light is constant. It doesn't matter if you're moving toward a light source or away from it, whether you're stationary or travelling at 90% of light speed yourself. You will always measure light, moving at exactly 300,000 kilometers per second relative to you. Always. This constancy is what makes relativity work, what forces time and space to be flexible so that light speed can remain fixed. And this is why, for more than a century, we've considered light the fastest thing in the universe. It's built into the architecture of space-time. Einstein's equations make it clear. Light speed isn't just the fastest speed we've observed. It's the fastest speed possible. It's the speed that massless particles must travel, the speed that nothing with mass can reach, the universal constant that defines causality itself. This feels final, doesn't it? Definitive. The kind of answer that closes the book on a question. We asked what's fastest, and physics gave us a clear, mathematically rigorous answer. Light, 300,000 kilometers per second. the cosmic speed limit, the ultimate velocity. And it would be the final answer too, except for one small detail we've been quietly ignoring. All of these speeds, the Parker Solar Probe, cosmic rays, photons themselves, are speeds through space. They're measurements of how fast objects move relative to other objects, or relative to the fabric of space-time around them. They're about travellers and their journeys, about things crossing distances. But what if the fastest thing isn't travelling? Ancient Norse mythology speaks of the Bifrost, the rainbow bridge connecting Midgard, the realm of humans, to Asgard, home of the gods. The bridge itself shimmers and shifts, carrying gods across impossible distances. But here's the interesting part. The Bifrost isn't described as something the gods walk across so much as something that connects realms that are fundamentally separated. The bridge itself is the crossing. The journey isn't about movement through space, but about the relationship between spaces. It's a strange concept, this idea that the medium matters as much as the traveller, that distance itself might be flexible, that the space between things could change in ways that have nothing to do with motion. The Norse, of course, were building mythology, not physics. But sometimes mythology stumbles onto something true about the cosmos, even if the mechanism is different than imagined. And in this case, they were right about one thing. The universe's greatest speeds have nothing to do with how fast things can travel. They have to do with the distances themselves. So we've established that light moves at 300,000 kilometers per second, and that this appears to be the universe's hard limit on speed. But before we complicate that comfortable certainty, let's look at what manages to get close, because while nothing with mass can reach light speed, some things, through the most violent processes the universe can muster, come close enough that the difference starts to feel academic. These are the members of what we might call the Almost Light Speed Club, and gaining membership requires either extraordinary violence or extraordinary engineering, usually both. Let's start with neutrinos, because neutrinos are genuinely strange particles even by the standards of particle physics, which is saying something. Neutrinos are elementary particles, fundamental bits of matter that aren't made of anything smaller. They have almost no mass. So little mass that for decades physicists thought they might be massless, like photons. They interact so weakly with normal matter that right now, as you listen to this, trillions of neutrinos are passing through your body every second. Through the Earth, through everything, they're streaming outward from the sun's core, where they are produced by nuclear fusion, and most of them pass through the entire sun, all that dense hot matter, without interacting with a single atom. When a massive star explodes in a supernova, it releases an absolutely staggering number of neutrinos. We're talking about 10 to the power of 58 neutrinos in a few seconds. That's a 1 with 58 zeros after it. More neutrinos than there are atoms in thousands of Earths. And these neutrinos, produced in the collapsing core, where matter reaches densities that would make a neutron star look fluffy, are moving at speeds so close to light that measuring the difference requires extraordinary precision. How close? Well, neutrinos with typical supernova energies travel at speeds within a tiny fraction of a percent of light speed. They're so close to the cosmic speed limit that if you raced a neutrino against a photon across the galaxy, a journey of 100,000 light-years, the neutrino would arrive maybe a few years later. Maybe. The exact delay depends on the neutrino's energy and its tiny, still not precisely measured mass. But we're talking about a photo finish in a race lasting 100,000 years. This is impressively fast, but it's also a reminder of how strict the speed limit is. Even particles with almost no mass, particles so ghostly they ignore normal matter entirely, still can't quite reach light speed. They're bound by the same rules as everything else with mass. Close is the best you can do. Then there's humanity's attempt to join this club, the Large Hadron Collider. The LHC is a ring 27 kilometers in circumference buried under the border between France and Switzerland. Inside this ring, protons, simple hydrogen nuclei, just a single proton each, are accelerated to speeds that require adding several nines after the decimal point before you find where they differ from the speed of light. We're talking about speeds so extreme that these protons, each about a billionth of a gram, carry the kinetic energy of a flying mosquito. Think about that for a moment. A mosquito weighs about 2 milligrams. A single proton in the LHC carries the same kinetic energy as that entire mosquito flying through the air. The energy is the same, but concentrated into something so small that if you could see it, it would still be invisible. It's smaller than the wavelength of visible light. This is what it takes to approach the speed limit. You need to compress absurd amounts of energy into tiny amounts of mass. At these speeds, relativity becomes impossible to ignore. From the proton's perspective, if it had one, which it doesn't, but we're anthropomorphizing particles now, so let's commit. Time is flowing thousands of times slower than it does for the physicists watching. The 27-kilometer ring it's racing around has contracted to just a few centimeters in its direction of motion. It's experiencing a completely different geometry than we are, living in a universe that's been compressed and stretched by its velocity. And yet, despite all this energy, despite all this engineering, despite literally building the most sophisticated machine humanity has ever constructed specifically to accelerate particles as fast as physically possible, the protons still aren't moving at light speed. They're close, extraordinarily close, but they're still on the wrong side of the speed limit, still separated from light by an impassable gap. This is what makes the speed of light special. It's not just fast, it's unreachable by anything with mass, no matter how much energy you invest. You can get closer, add more particle accelerators, make them bigger, pump in more energy, but you'll never quite get there. The gap shrinks, but it never closes. It's asymptotic. You're chasing something you can approach forever without reaching. Nature, of course, has particle accelerators that make the LHC look quaint. Consider the accretion disk around a black hole. Matter falling toward a black hole doesn't just fall straight in. Conservation of angular momentum means it spirals inward, forming a disk of gas and dust that orbits closer and closer to the event horizon. As this matter spirals inward, gravitational energy converts to heat and kinetic energy. The inner regions of the disk reach temperatures of millions of degrees. Atoms are ionized into plasma. Magnetic fields twist and snap, and jets of this plasma get flung outward along the black hole's rotation axis at speeds that, once again, require multiple nines to distinguish from light speed. These jets can extend for thousands of light years, carving channels through intergalactic space, pumping energy into the cosmic medium at rates that dwarf the total energy output of entire galaxies. They're visible across billions of light years. They're some of the most luminous phenomena in the universe, and they're moving at relativistic speeds, speeds where relativity's effects dominate, where time and space behave strangely, where the simple Newtonian physics of everyday experience breaks down completely. But, and this is the pattern we keep seeing, they're still not quite at light speed. They're close. Close enough that the difference barely matters for most purposes. But physics doesn't care about close enough. There's a difference between moving at relativistic speeds and moving at light speed, and that difference is fundamental. Particles moving at 99% of light speed experience time dilation and length contraction. Photons moving at exactly light speed experience no time at all. From a photon's perspective, if it had one, its entire journey from emission to absorption happens instantaneously. It's created and destroyed in the same moment, travelling across billions of light years in zero time. This is the divide. This is what separates the almost light speed club from actual light speed, and it's unbridgeable if you have mass. The most extreme example of nature's particle acceleration comes from gamma-ray bursts, the most energetic explosions in the universe aside from the Big Bang itself. These occur when massive stars collapse into black holes, or when neutron stars collide and merge. For a few seconds to a few minutes, a gamma-ray burst can outshine the entire rest of the universe combined in gamma rays. The energy released in those brief moments exceeds what our sun will emit across its entire 10 billion year lifetime. The jets from these bursts contain matter and radiation, moving at speeds so close to light that physicists describe them with a special term, ultra-relativistic. Not just relativistic, ultra-relativistic. So close to light speed that the Lorentz factor, the number that describes time dilation and length contraction, reaches values in the hundreds or thousands. From our perspective, particles in these jets are racing at speeds where you need to write out percentages, with 4 or 5 nines after the decimal point before you encounter a number that isn't 9. These are the fastest massive particles we know about, the cosmic speed champions, the things that have pushed closer to light speed than anything else with mass, and they're still losing the race against photons. This might seem frustrating. Why have a speed limit if everything interesting happens just below it? Why make light speed special if massive particles can get so close that the difference is negligible for most practical purposes? But that's exactly the point. The speed limit isn't there to be frustrating. It's there because it's woven into how causality works. Light speed isn't just the fastest speed. It's the speed at which cause and effect propagate. It's the speed at which information can travel. If you could exceed it, you could theoretically send signals backward in time, creating paradoxes that would break the logical structure of the universe. The speed limit exists because time needs to have a direction, because effects need to follow causes, because the universe needs to make sense. So relativity enforces the limit not through barriers or walls, but through mathematics. As you accelerate, your mass effectively increases, requiring more and more energy for less and less additional speed. Time dilation means you're experiencing less and less time for each increment of coordinate time that passes. Space contracts ahead of you. The universe literally warps around you to prevent you from reaching the forbidden velocity. It's elegant, really. The universe doesn't say you can't go this fast and leave it at that. It says you can try, and the closer you get, the more the universe will bend to stop you, until you'd need infinite energy to make that final step. It's not a wall. It's an asymptote, a limit you can approach forever without reaching. Ancient Chinese astronomers had a concept called Tianyuan, the unreachable celestial distance. It referred to the vast separation between the mortal realm and the heavens, a boundary not of space, but of fundamental incompatibility. Mortals couldn't reach the heavens, not because the distance was too great, but because the heavens existed in a fundamentally different mode of being. The separation was built into the nature of things. The speed of light is our Tianyuan. It's not that we lack the technology or energy to reach it, though we certainly do. It's that reaching it would require us to become something fundamentally different. Massless, timeless. Travelling zero distance in zero time, we're separated from light speed, not by engineering challenges, but by the architecture of reality itself. and for more than a century, this seemed like the final word on cosmic speed. Massive particles can get arbitrarily close to light speed but never reach it. Massless particles must travel at exactly light speed. Nothing goes faster. The speed limit is absolute, enforced by the very structure of space-time, unbreakable under any circumstances. Which would be true too if we were asking the right question. But we're not quite asking the right question yet, because all of these speeds, neutrinos, protons, plasma jets, gamma-ray bursts, are speeds of objects moving through space-time. They're about travellers and journeys, about things crossing distances while space-time remains, we assume, a fixed stage for the action. That assumption is about to become very interesting. In the early 1970s, radio astronomers started noticing something deeply strange. They were observing quasars, those extraordinarily luminous galactic cores powered by supermassive black holes, and measuring the jets of material streaming outward from them. And according to their measurements, some of these jets were moving faster than light. Not close to light speed, not approaching it asymptotically. Faster, multiple times faster in some cases. Components of these jets appeared to be separating from each other at velocities that, by all calculations, exceeded the cosmic speed limit we'd just spent 2 chapters establishing was impossible to exceed. This was, to put it mildly, concerning. Einstein's theory of special relativity had been tested extensively for decades. It worked. It predicted the right outcomes. Time dilation had been measured. Length contraction had been confirmed. The constancy of light speed was well established. And now here were observations that seemed to contradict the whole framework. Either the measurements were wrong, or relativity was wrong, or something very interesting was happening that nobody had quite thought through yet. Spoiler, it was the third option. Nothing was breaking the speed limit, but the universe was doing something clever with geometry and timing that created a very convincing illusion. Let's look at a specific example to understand what was happening. One of the first and most famous cases was a quasar called 3C273, located about 2.5 billion light-years away in the constellation Virgo. It's extremely bright, the most luminous object in that region of sky, and it has a visible jet of material streaming outward from its central black hole. Radio observations show that bright knots of material in this jet were moving outward, and by measuring their positions over time, astronomers could calculate their velocity. The velocity appeared to be several times the speed of light. Here's what was actually happening, and why it looked impossible. Imagine a jet of material shooting outward from a quasar at, let's say, 95% of the speed of light. That's relativistic, certainly, but it's not faster than light. It's well within what physics allows. Now imagine that this jet isn't shooting directly away from us, but at a small angle, maybe 20 degrees from our line of sight. So it's heading mostly toward us, but not quite directly. The jet is emitting light the entire time it travels. At the beginning of our observation period, the jet emits a photon from position A. The jet then races forward, and sometime later it emits another photon from position B, which is closer to us. Both photons travel toward Earth at the speed of light. They have no choice. But the second photon has a head start. It was emitted from a position closer to us, which means it has less distance to travel. Now here's where the illusion emerges. Because the jet is moving so fast and at such an angle, the second photon doesn't just have a head start, it has a substantial head start. The jet has been racing toward us at 95% of light speed while the first photon was travelling. By the time the second photon is emitted, the distance it needs to travel is significantly shorter than the distance the first photon had to travel. When both photons reach Earth, Arriving at different times naturally, we measure the time difference and the apparent distance the jet has travelled between the two emissions. And because of the geometry, because of that head start, the jet appears to have covered the distance much faster than it actually did. From our perspective, watching the jet move across the sky, it looks like it's moving faster than the speed of light. It's rather like watching someone run toward you while carrying a flashlight. If they're running fast enough and at the right angle, the light they're emitting at different points along their path will reach you with timing that makes them seem to be covering ground impossibly quickly. The runner isn't actually exceeding any speed limits. You're just seeing a compressed timeline because of how light travel time works. This phenomenon has a delightfully technical name: superluminal motion. Not faster than light motion, which would be genuinely impossible, but apparent faster than light motion. Motion that looks superluminal from our perspective, but isn't actually breaking any physical laws. It's a geometric illusion created by extreme velocities and fortunate viewing angles. Once astronomers worked out what was happening, they could use the apparent velocity to actually calculate the real velocity of the jet and its angle relative to our line of sight. If you measure how fast something appears to be moving, and you know the maximum real speed it could have, the geometry constrains the possibilities. It becomes a diagnostic tool rather than a paradox. Those jets that appeared to be moving at 5 times the speed of light, they were actually moving at about 95% of light speed, aimed nearly but not quite toward us. The effect is most pronounced when the jet is moving at speeds very close to light speed and at angles between about 10 and 30 degrees from our line of sight. Too direct, and there's no angular motion to measure. The jet is just coming straight at us. Too oblique, and the foreshortening effect isn't dramatic enough to create the illusion. But in that sweet spot, with jets moving at relativistic speeds at just the right angle, the apparent velocity can be many times the speed of light. It's a reminder of how much our perception of the universe depends on perspective. We're not seeing these jets directly. We're seeing light that left them millions or billions of years ago, and we're inferring motion from changes in position over time. But time and position are already being warped by relativity, and when you add in light travel time and geometry, what we observe can be very different from what's actually happening. This also explains why we see superluminal motion in some quasar jets but not in others. It's not that some quasars have faster jets, though they do vary. It's that we're seeing them from different angles. A jet moving at 95% of light speed will look superluminal if it's aimed nearly toward us. But if we're viewing it edge-on or from the side, we'll measure its true velocity, which is firmly subluminal. The jets themselves aren't doing anything different. Our viewing geometry is. So nothing is actually breaking Einstein's laws. The cosmic speed limit remains intact. But this episode introduced an important realization. The universe can create situations where the speed limit seems to be violated from certain perspectives, even though it's being perfectly respected in reality. The rules are absolute, but our perception of them can be bent by geometry and timing in ways that make impossible things appear possible. This is our first hint that speed, or at least our perception of it, is more complicated than simple velocities, that what we see and what's actually happening can diverge in interesting ways when relativity and geometry interact, that the question "how fast is that moving?" might not have a single, simple answer that all observers agree on. The universe, it turns out, is comfortable with this ambiguity. Physics has clear rules, but those rules can produce outcomes that look paradoxical from certain angles. The speed limit exists, it's real, it's enforced, and yet, under the right circumstances, things can appear to exceed it without actually doing so. If this makes you slightly uncomfortable, if you're feeling like the universe's rules are starting to feel a bit more flexible than you'd like, that's actually perfect, because we're building towards something bigger. These apparent violations, these geometric tricks, these perspective-dependent observations, they're all preparing us for a genuine case where something really does exceed the speed of light. Not apparently, actually, without breaking relativity, without paradoxes. But we're not there yet. Ancient Polynesian navigators had a profound understanding of perspective and relative motion. They would sail for days across open ocean with no landmarks, navigating by stars and waves and the flights of birds. And they understood something crucial, the relationship between observer and observed. When you sail toward the horizon, the sky and sea appear to drift apart, the boundary between them receding as you approach. Distance becomes slippery. What seems close reveals itself as far. What seems unreachable might be just beyond the next swell. They knew that motion across the ocean isn't about fixed positions, but about relationships, between your vessel and the stars, between the waves and the wind, between where you are and where you're trying to go. The same wave that's ahead of you is behind you moments later, not because the wave moved backward, but because you moved forward. Perspective shapes reality. Superluminal motion is similar. The jets haven't exceeded light speed, but from our perspective, watching from billions of light years away with light as our only messenger, they appear to have done something impossible. The reality and the observation diverge, and that divergence teaches us to be careful about assuming that what we observe is what's actually happening, especially when dealing with extreme velocities and cosmic distances. So we have our first encounter with faster-than-light motion, and it turned out to be an illusion, a fascinating, instructive illusion that taught us about geometry and perspective, but an illusion nonetheless. The speed limit held firm. Einstein's relativity remained unbroken. The universe played a trick on us, but only a trick of perception, which means we can continue trusting that nothing moves faster than light, that the cosmic speed limit is absolute, that the universe makes sense and follows consistent rules. At least nothing moves faster than light through space. That last bit is going to become important. But now, let's talk about something different. Actual objects. Massive, tangible things you could theoretically point a telescope at, moving at velocities that are, by any reasonable standard, absolutely absurd. Let's talk about hypervelocity stars. These are stars that have been flung out of our galaxy at speeds of several hundred to over 1,000 kilometers per second, fast enough to escape the Milky Way's gravitational pull entirely, fast enough to be on a one-way journey into intergalactic space, fast enough that they make our fastest spacecraft look like they're standing still, and they achieve these speeds not through engines or rocket fuel, but through gravitational violence of a very specific and dramatic kind. To understand how this happens, we need to visit the center of our galaxy. At the heart of the Milky Way, about 26,000 light-years from Earth in the direction of the constellation Sagittarius, sits Sagittarius A star. Not actually a star, despite the name, but a supermassive black hole containing about 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Around this black hole, stars orbit in a dense, chaotic swarm, thousands of stars packed into a region of space that, by galactic standards, is extraordinarily compact. It's a cosmic mosh pit, and the black hole is the bouncer. Occasionally, and by occasionally I mean every few 100,000 years or so, a binary star system wanders too close to this black hole. Binary systems are pairs of stars orbiting each other, bound together by their mutual gravity. They're extremely common. More than half of all star systems in the galaxy are binaries, or higher-order multiples. So having them drift into the galactic center isn't particularly unusual. What happens next is a gravitational interaction that can only be described as violent in its elegance. As the binary system approaches the black hole's gravity begins to dominate. The two stars, which had been happily orbiting each other for millions or billions of years, suddenly find themselves in a much stronger gravitational field. The black hole pulls harder on whichever star is closer to it, and this differential pull starts to tear the binary apart. The system becomes gravitationally unstable. In the most dramatic cases, one star gets captured into orbit around the black hole. It's been caught, doomed to circle Sagittarius A star in an increasingly tight orbit until it's eventually torn apart or consumed. Its companion, however, experiences something completely different. When one star is captured, the orbital energy of the binary system has to go somewhere. Energy is conserved. It's one of those non-negotiable rules the universe is quite strict about. The energy that was keeping both stars in mutual orbit doesn't just disappear when one star is captured. Instead, it gets transferred to the other star in the form of kinetic energy. The remaining star gets flung outward like a stone from a slingshot, accelerated to tremendous velocity by the same gravitational forces that captured its companion. This is called a gravitational slingshot, and it's spectacularly effective. The star doesn't just drift away. It doesn't amble off into the galactic suburbs. It races outward at speeds that can exceed 1,000 kilometers per second. Fast enough to escape the Milky Way's gravity entirely, fast enough to become an intergalactic traveler, fast enough to cross the distance from Earth to the Moon in about 4 minutes. The first hypervelocity star was discovered in 2005, though astronomers had predicted their existence decades earlier. Since then, we've found dozens more, and we suspect there are millions of them out there, most too faint and distant to detect easily. They're cosmic refugees, stars that had the extraordinarily bad luck to wander too close to the galactic center, with a companion, and ended up paying for it with permanent exile. One of the fastest we've found is designated S5HVS1, discovered in 2019. It's travelling at roughly 1,700 kilometers per second, about 0.5% of the speed of light. By stellar standards, this is breathtaking. Most stars in the galaxy orbit the galactic center at around 200 kilometers per second. The Sun manages about 230. S5HVS1 is moving nearly 8 times faster than our Sun's orbital velocity. It's not just escaping the galaxy, it's fleeing. At this velocity, S5HVS1 will travel roughly 33,000 light-years every million years. Give it enough time, say 100 million years, and it will be over 3 million light-years away, well into intergalactic space, forever separated from the galaxy that birthed it. It's a one-way ticket. There's no coming back from these velocities once you've escaped the galaxy's gravitational well. What's remarkable about hypervelocity stars isn't just their speed, though that is impressive, it's that they're entire stars moving this fast. Not particles, not plasma, not ephemeral jets of matter. These are objects with perhaps half the mass of our Sun, containing something like 10 to the power of 57 atoms, all moving together at over 1,000 kilometers per second. The sheer momentum involved is staggering. If you could somehow harness one of these stars, the kinetic energy would dwarf anything humanity has ever generated by factors that make astronomical seem like an understatement. But here's what keeps hypervelocity stars from being the final answer to our question about cosmic speed. Even at 1700 kilometers per second, even at 0.5% of light speed, they're still nowhere close to the actual speed limit. They're fast by stellar standards. They're fast by any everyday standard. They're so fast that if you could somehow ride one, relativistic effects would become barely measurable. Time would flow perhaps a few parts per million slower for you than for someone at rest. But they're still fundamentally slow by cosmic standards. A photon travelling alongside S5 HVS1 would leave it in the dust almost instantly. After 1 second, the photon would be 300,000 kilometres ahead. After 1 hour, it would be over 1 billion kilometres ahead, 7 times the distance from Earth to the Sun. After 1 year, the photon would have travelled a full light year, while the star managed barely 2/100ths of a light year. They're not even in the same race, really. This is the pattern we keep encountering. Each time we find something impressively fast, cosmic rays, jets from black holes, stars flung from galactic cores, we discover that while it's fast by certain standards, it's still crawling compared to light, and light remains the speed limit, the impassable boundary, the ultimate velocity. Still, there's something poetic about hypervelocity stars. They're cosmic wanderers, forever travelling, never arriving anywhere in particular. They left their galaxy behind millions of years ago and will spend the rest of their lives, potentially billions of years, coasting through the void between galaxies, slowly running out of hydrogen fuel, gradually cooling and dimming, dying alone in the darkness between island universes. It's beautiful in a melancholic way. These stars will see things no other stars see. They'll watch galaxies from outside, observe the cosmic web from between its strands. They're explorers by accident, refugees by circumstance, travellers without a destination. In Hindu mythology, there are the Ashvins, divine twin horsemen who race across the sky, pulling the dawn. They move faster than mortal perception can follow, travelling between realms, forever in motion. They're described as the swiftest of all beings, crossing impossible distances before the sun rises. They're messengers, healers, rescuers, defined entirely by their endless journey. They belong nowhere and everywhere, racing perpetually across the cosmos. Hypervelocity stars are our Ashvins, not divine certainly, but swift beyond ordinary measure, racing through the galaxy and beyond, never settling, never stopping, forever fleeing the gravitational catastrophe that flung them outward. They're defined by their motion, by their velocity, by their permanent exile from the galactic society they once belonged to. And like the Ashvins, they represent the fastest things we can point to and say, look, that physical object is moving at that absurd speed through space. They're real, they're measurable, they're not illusions or geometric tricks, they're actual stars, actual matter, actually moving at these tremendous velocities, which makes them excellent candidates for the title of fastest thing in the universe. They're certainly the fastest massive objects we know about that aren't particles. They're moving at speeds that boggle the mind. They're dramatic and poetic and strange. And yet, 1700 kilometers per second, 0.5% of light speed, impressive by any reasonable standard, fast enough to escape an entire galaxy, fast enough to coast through intergalactic space for billions of years. And compared to what's actually racing through the cosmos, these cosmic escape artists might as well be standing still. But first, we need to go back to the very beginning. Not to the Big Bang itself. That moment is still somewhat mysterious, wrapped in physics we don't fully understand, but to what happened immediately after. And by immediately, I mean a time so short that calling it a fraction of a second seems generous, We're talking about events that occurred when the universe was a trillionth of a trillionth of a trillionth of a second old. At these timescales, human intuition completely breaks down. A trillionth of a second is already incomprehensibly brief. Light travels about a third of a millimetre in that time. But a trillionth of a trillionth? We're in territory where numbers stop meaning anything tangible and become purely abstract mathematical constructs. The universe at this age was so young that calling it an infant would be like calling the Pacific Ocean damp. This is when something extraordinary happened. Something that, when cosmologists first proposed it in the 1980s, seemed so extreme that it took years for the physics community to accept it as anything more than interesting speculation. But the evidence kept mounting, and now it's a core part of our understanding of how the universe works. The universe underwent a period of inflation, not gradual expansion, not steady growth. Inflation, exponential runaway expansion, at speeds that make everything we've discussed so far look like it's frozen in place. Here's what inflation means in the most literal sense. The universe doubled in size, then doubled again, then doubled again, over and over in rapid succession. The doubling happened roughly every hundredth of a trillionth of a trillionth of a second. That's 10 to the negative 34 seconds, if you prefer exponential notation. Either way, it's a time span so brief that light, moving at its maximum possible speed, would travel a distance smaller than the diameter of a proton. In that incomprehensibly brief interval, the universe doubled, and then doubled again, and again. And this continued for perhaps 10 to the negative 32 seconds, 100 times longer than each individual doubling period, but still far, far shorter than anything we can meaningfully relate to human experience. By the time inflation ended, the universe had doubled somewhere between 60 and 100 times, depending on which model of inflation you prefer. Let's use 80 doublings as a reasonable middle estimate. That means the universe expanded by a factor of 2 to the power of 80. 2 to the power of 80 is, well, it's a large number, roughly 1,000,000 trillion trillion. If the universe started smaller than a proton and expanded by this factor, it would end up larger than a grapefruit. Some models suggest it grew even larger, perhaps to the size of our solar system. The exact final size depends on how big the universe was when inflation started, and exactly how many doublings occurred, both of which are still matters of active research and some debate. But here's the thing that matters more than the specific numbers. This expansion happened faster than the speed of light. Much, much faster. If you picked 2 points in the early universe and watched them during inflation, they would separate from each other at speeds that make light look glacial. We're not talking about twice the speed of light, or 10 times, or even 1,000 times. We're talking about expansion rates that exceeded the speed of light by factors so large that writing them out would require more zeros than I care to count. Now let's pause here, because this seems to directly contradict everything we've established about the cosmic speed limit. We've spent several chapters explaining why nothing can exceed the speed of light, how relativity enforces this limit through time dilation and length contraction, how even the most violent cosmic processes can only approach light speed without reaching it. And now I'm telling you that the universe itself expanded faster than light during its first fraction of a second. This is where we need to be very careful about language and very precise about what we mean by speed. During inflation, nothing moved through space faster than light. Not one thing. The speed limit remained absolute. Relativity was not violated. Einstein's equations continued to hold perfectly. What happened was something more subtle and, in some ways, more strange. Space itself expanded. This is the crucial distinction, and it's worth sitting with for a moment because it's the key to everything that follows. When we talk about the speed of light as a cosmic limit, we're talking about motion through space, objects moving relative to each other, particles travelling from one point to another, matter or energy crossing distances. The speed limit applies to travellers and their journeys. It applies to things moving through the fabric of space-time. But the speed limit doesn't apply to space itself. Space isn't a thing travelling through another medium. It's not moving from point A to point B. It's the stage on which motion happens, the canvas on which the universe is painted. And that stage can change size. That canvas can stretch. There's no law of physics that limits how fast it can do so. The best analogy, and it's imperfect, all analogies are, is rising bread dough. Imagine you've got a lump of dough with raisins scattered through it. As the dough rises, the raisins move apart from each other. But the raisins themselves aren't travelling through the dough. They're not swimming or pushing their way through yeast and flour. They're staying put relative to the dough immediately around them. It's the dough itself that's expanding, carrying the raisins along with it. Now imagine the dough rises very quickly, exponentially quickly, doubling in volume every second. Raisins that were centimetres apart would suddenly be metres apart, then kilometres apart, then thousands of kilometres apart. The separation velocity, how fast the distance between raisins grows, can easily exceed any speed limit you care to impose on objects moving through the dough. But no raisin is actually moving. They're all stationary relative to their local bit of dough. The expansion is what's creating the separation. This is what happened during inflation. Except instead of dough we have space-time, instead of raisins we have quantum fluctuations and energy fields, and instead of rising over minutes we're talking about expansion over impossibly brief fractions of a second. The fabric of space expanded exponentially, carrying everything embedded in it along for the ride. Nothing moved. Everything separated. And the separation happened at rates that vastly exceeded the speed of light. This is completely consistent with relativity. Einstein's equations not only allow for this, they predict it under the right conditions. When space itself expands, it creates recession velocity, the rate at which distance grows between objects. And there's no limit on how large recession velocity can be. It's not governed by the same rules that govern motion through space. It's a different category of phenomenon entirely. Cosmologists sometimes describe this using two different concepts, proper distance and co-moving distance. Proper distance is what we normally think of as distance, the actual physical separation between 2 points measured at a specific moment in time. Co-moving distance accounts for the expansion of space, describing where objects would be if the expansion were somehow removed. During inflation, proper distances grew at faster than light speeds, but co-moving distances remained constant. Objects that were close together before inflation were still close together in co-moving terms afterward, even though the proper distance between them had become enormous. I realise this is getting abstract, so let me put it more concretely. Imagine two particles sitting next to each other when inflation begins. They're separated by, let's say, the diameter of a proton. They're not moving relative to each other. There's no velocity, no momentum carrying them apart. Then inflation happens. The space between them expands by a factor of 1,000,000 trillion trillion. Now they're separated by distances measured in meters or kilometers, depending on exactly how inflation proceeded. But neither particle moved, neither crossed space. They remained stationary in their local reference frame. Space simply grew between them. From each particle's perspective, if quantum particles had perspectives, which they don't, but humour me, Nothing happened. They didn't accelerate. They didn't feel forces. They just found themselves, when inflation ended, very far from where they used to be very close to. This is why inflation doesn't violate relativity. Relativity says nothing can move through space-time faster than light. Inflation didn't move anything through space-time. It expanded space-time itself, and there's no law against that. The distinction matters. It's not a technicality or a loophole. It's a fundamental difference in the type of phenomenon we're discussing. In Hindu cosmology, there's a story about Vamana, one of the avatars of Vishnu. Vamana appears as a small Brahmin and asks the demon king, Bali, for a gift of land, just as much as he can cover in 3 strides. Bali, amused by the humble request, agrees. Vamana then reveals his cosmic form and takes 3 steps that span the universe. The first step covers the earth. The second step covers the heavens. The third step encompasses everything beyond. What's interesting about this myth isn't that Vamana moves quickly. It's that each stride stretches reality itself. He doesn't run across vast distances. He doesn't fly at impossible speeds. Each step expands, encompassing more than should be possible to cross in a single motion. The universe accommodates him. Space itself adjusts to allow the impossible. Inflation is Vamana's stride. It's not the universe running somewhere. It's the universe expanding, stretching, accommodating more space than existed a moment before. Reality adjusts, distances grow, and nothing moves at all. So that's inflation, the universe's first and most dramatic example of faster-than-light expansion. It happened in the first tiny fraction of a second after the Big Bang, lasted for an equally tiny fraction of a second, and left us with a universe vastly larger than it would have been otherwise. It seeded the structures that would eventually become galaxies and galaxy clusters. It smoothed out irregularities, creating the remarkably uniform universe we observe on large scales. And it demonstrated that space itself can expand at any rate, limited by nothing, bound by no speed limit. So inflation happened in the first tiny fraction of a second, expanding space at rates that dwarf anything we can meaningfully comprehend. Then it stopped. The exponential doubling ended, and the universe continued expanding at more sedate rates. For billions of years, space has been growing, but gradually, calmly, without the violence of that initial burst. Except, here's what's interesting. That expansion never stopped, and we can see it, not just as evidence in the cosmic microwave background or in the distribution of galaxies, but as actual motion. Right now, as you listen to this, galaxies across the universe are moving away from us, all of them, in every direction, and the pattern of their motion reveals something profound about how space works. Let's go back to the 1920s, to Mount Wilson Observatory perched in the mountains above Los Angeles. At the time, it housed the largest telescope in the world, a 100-inch reflector that could gather enough light to examine distant galaxies in detail. And working at this telescope was an astronomer named Edwin Hubble, who was about to make a discovery that would fundamentally change how we understand the universe. Hubble was measuring the light from distant galaxies, examining their spectra, the rainbow of colours produced when you split their light through a prism or diffraction grating. Each element produces characteristic patterns of bright and dark lines in its spectrum. Hydrogen produces one pattern, helium another, oxygen a third. These patterns are like fingerprints, unique and recognizable. When you look at a galaxy's spectrum, you can identify which elements it contains just by matching the patterns. But Hubble noticed something strange. The patterns were there, recognizable and familiar, but they were shifted. The lines that should have appeared at specific wavelengths, specific colors, were showing up at longer wavelengths instead. Everything was shifted toward the red end of the spectrum, a phenomenon astronomers call redshift. This wasn't a mystery. Physicists already understood redshift through the Doppler effect, the same phenomenon that makes an ambulance siren sound higher-pitched as it approaches and lower-pitched as it recedes. When a source of waves moves away from you, the waves get stretched. Their wavelength increases, their frequency decreases. For sound, this means lower pitch. For light, this means a shift toward red, the longest wavelength color visible to human eyes. So galaxies showing redshift meant galaxies moving away. That much was clear. What surprised Hubble was the pattern. The farther away a galaxy was, the faster it appeared to be receding. Not randomly, not with occasional exceptions, systematically, predictably, with mathematical precision. Double the distance, double the recession velocity. Triple the distance, triple the velocity. The relationship was linear, perfect, elegant. Hubble published this relationship in 1929, and it transformed cosmology. What had been a static universe in most people's conception, eternal, unchanging, fixed, was revealed to be dynamic, expanding, growing. And the expansion followed a simple rule, now called Hubble's law. Recession velocity equals the Hubble constant times distance, or in mathematical notation, v equals h0 times d. That h0, the Hubble constant, is one of the most important numbers in cosmology. It tells us how fast the universe is expanding right now, expressed as velocity per unit distance. The current best measurements put it at around 70 kilometers per second per megaparsec, which is a delightfully awkward unit that requires some unpacking. A megaparsec is a unit of cosmic distance. 1 parsec is about 3.26 light-years, roughly 30 trillion kilometers. A megaparsec is a million parsecs, or about 3.26 million light-years. It's the kind of distance that separates nearby galaxy clusters. Huge by any terrestrial standard, but manageable by cosmic ones. So when we say the Hubble constant is 70 kilometers per second per megaparsec, we mean that for every megaparsec of distance between us and a galaxy, that galaxy is receding at an additional 70 kilometers per second. A galaxy 1 megaparsec away recedes at 70 kilometers per second. A galaxy 2 megaparsecs away recedes at 140 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second, and so on. Let's do some arithmetic to see where this leads. Consider a galaxy 1 billion light-years away. That's about 300 megaparsecs. According to Hubble's law, it should be receding at 70 times 300, 21,000 kilometers per second. That's 7% of the speed of light. Quite fast, faster than any hypervelocity star, but still solidly subluminal, well within what relativity allows. Now consider a galaxy 5 billion light-years away. That's about 1,500 megaparsecs. Its recession velocity should be 70 times 1,500, 105,000 kilometers per second. 35% of the speed of light. Getting faster, starting to approach relativistic velocities. A galaxy 10 billion light-years away? 3,000 megaparsecs, 210,000 kilometers per second, 70% of the speed of light. We're deep into relativistic territory now, approaching the speeds of cosmic rays and gamma-ray burst jets. You can probably see where this is going. Hubble's law is linear. There's no flattening, no plateau, no speed limit built into the equation. It just keeps going. Distance increases, velocity increases proportionally, which means that at some distance, some specific calculable distance, the recession velocity equals the speed of light, And beyond that distance, the recession velocity exceeds the speed of light. We can calculate exactly where this happens. Take the speed of light, 300,000 kilometers per second, and divide by the Hubble constant, 70 kilometers per second per megaparsec. The result is about 4,300 megaparsecs, or roughly 14 billion light-years. At that distance, according to Hubble's law, galaxies are receding at exactly the speed of light. And beyond that distance, they're receding faster. Now, before you object that this violates everything we've discussed about the cosmic speed limit, remember what we learned in the last chapter. These galaxies aren't moving through space at these velocities. They're not traveling, not racing, not journeying anywhere. Space itself is expanding between us and them. The recession velocity is a measure of how fast the distance is growing, not how fast anything is moving through space-time. It's the same phenomenon as inflation, just much, much slower. During inflation, space doubled every tiny fraction of a second. Now, space expands much more gradually. It takes tens of millions of years for distances to increase noticeably. But the mechanism is the same. Space grows. Things embedded in space get carried along, and the separation between them increases at a rate determined by how much space is expanding and how far apart they are. This is why the recession velocity follows Hubble's law so precisely. It's not that distant galaxies are fleeing from us. We're not special. There's no cosmic repulsion aimed at the Milky Way. It's that space is expanding everywhere, uniformly in all directions. The farther apart two objects are, the more expanding space sits between them, and therefore the faster their separation grows. It's a geometric consequence of uniform expansion. If you were sitting in any other galaxy in the universe, looking out at the cosmos, you'd see exactly the same pattern. Galaxies receding in all directions, velocities proportional to distance, the whole universe appearing to expand away from your position. Everyone sees themselves at the center of the expansion, not because they are, but because expansion has no center. It's happening everywhere simultaneously. The redshift we observe isn't quite the same as the Doppler shift from object moving through space, though it produces similar effects. It's more accurately described as cosmological redshift, light being stretched by the expansion of space as it travels. A photon leaves a distant galaxy with a certain wavelength. As it crosses the expanding universe toward us, the space it's traveling through is growing. The wavelength gets stretched along with everything else. By the time the photon reaches us, its wavelength is longer, redshifted, not because the galaxy was moving when it emitted the photon, but because space expanded during the photon's journey. This distinction matters for distant galaxies, where recession velocities approach or exceed light speed. You can't have a Doppler shift corresponding to faster-than-light motion through space. That would require impossible physics. But you can have cosmological redshift corresponding to faster-than-light recession due to expansion. The math works out differently, the physical interpretation is different, and relativity remains unviolated. There's a beautiful historical parallel here. In the 11th century, a Persian scholar named al-Biruni wanted to calculate the radius of the Earth. He climbed a mountain, measured the angle to the horizon, used the height of the mountain, and through geometry alone, calculated Earth's radius to remarkable accuracy. He measured something vast and seemingly unreachable, using only careful observation and mathematics. Hubble did something similar. He couldn't travel to distant galaxies. He couldn't measure their distances directly, but through careful observation of their light, measuring redshift, calculating distance through other means like standard candles and Cepheid variable stars, he mapped the expansion of the universe. He measured the unmeasurable. He quantified the growth of space itself, using nothing but light that had travelled for millions or billions of years to reach his telescope. Humanity has always tried to measure the unreachable, to quantify the cosmic, to understand distances and scales beyond our direct experience. Al-Biruni measured Earth's curvature from a mountaintop. Hubble measured the universe's expansion from a mountain observatory. Both found that the cosmos was larger and stranger than previously imagined. Both discovered that careful observation could reveal truths about scales no human could ever directly traverse. So here's where we are. We've established that space expands. We've shown that this expansion creates recession velocities proportional to distance. We've calculated that at about 14 billion light-years, recession velocities reach the speed of light. And we've noted that Hubble's law doesn't stop there. It just keeps going, implying recession velocities that exceed light speed for sufficiently distant galaxies. And all of this is happening right now, not in the early universe, not during some exotic phase of cosmic evolution. Now, today, as you listen to this, across the observable universe, space is expanding, distances are growing, and recession velocities are piling up in proportion to separation. Let's return to Hubble's law one more time. Recession velocity equals the Hubble constant times distance. V equals h0 times d. Simple, linear, elegant. And as we established in the last chapter, this relationship doesn't plateau, doesn't level off, doesn't acknowledge any upper limit. It just continues. Distance increases, velocity increases proportionally, and at some specific distance, the mathematics leads us somewhere remarkable. We calculated that at roughly 14 billion light-years, about 4,300 megaparsecs, the recession velocity reaches 300,000 kilometers per second. The speed of light. Galaxies at this distance are receding at exactly the cosmic speed limit. But Hubble's law doesn't stop there. There's no special clause, no footnote saying void after 14 billion light-years. The equation continues working, and what it tells us is that galaxies farther than 14 billion light-years are receding faster than the speed of light. A galaxy 15 billion light-years away, receding at about 320,000 kilometers per second, faster than light by roughly 6%. 20 billion light-years, 430,000 kilometers per second, about 1.4 times the speed of light. 30 billion light-years, 640,000 kilometers per second, more than twice the speed of light. The numbers just keep growing, 3 times the speed of light, 5 times, 10 times. There are regions of the universe, regions we can see, regions whose light has reached us, where space is expanding so fast that the recession velocities are dozens of times the speed of light. Not approximately, not in some technical sense. Actually, measurably, observably. Let's sit with this for a moment. We've spent this entire journey cataloguing fast things. The Parker Solar Probe at 190 kilometers per second, hypervelocity stars at 1700 kilometers per second, cosmic rays at speeds so close to light that you need multiple decimal places to express the difference. And all of these velocities, impressive as they are utterly dwarfed by the recession velocities created by cosmic expansion. The fastest hypervelocity star we know about is moving at about 0.5% of light speed. The fastest recession velocity we can observe is dozens of times the speed of light. They're not even close. It's not a competition. The expansion of space wins by margins so large that comparing them feels almost absurd. So here's the answer to our original question. What's the fastest thing in the universe? It's not a spacecraft, not a particle, not a star or a jet or a burst of gamma rays. It's not light itself, even though light moves at the cosmic speed limit. The fastest thing in the universe is something we barely think of as a thing at all. It's the expansion of space. Space itself, the fabric of the universe, the stage on which everything else plays out, is expanding, and in doing so, it's creating separation velocities that exceed every other speed we've discussed, not by a little, by enormous factors. The universe is racing away from itself faster than anything in it could ever travel. This is the twist. This is what we've been building toward. The fastest thing isn't moving. It's not crossing distances or journeying from one point to another. It's the distance itself, growing, expanding, creating separation at rates that make light look slow. And this doesn't violate relativity, not even slightly. Einstein's speed limit, that nothing can move through space-time faster than light, remains perfectly intact. The key word there is through. Objects moving through space are bound by the speed limit. Space itself expanding isn't subject to that constraint. The rules apply to travellers, not to the road they're travelling on. When the road itself stretches, when new distance appears between points that were previously close together, that's not motion, that's geometry changing. Let me phrase this a different way because it's worth approaching from multiple angles. Relativity says that no signal, no information, no cause and effect relationship can propagate faster than light. This is crucial for maintaining causality, for ensuring that effects follow causes, for keeping time coherent. And this rule is never violated. If you're sitting in a galaxy 20 billion light-years away, a galaxy receding from us at faster than light speed, you still can't send us a signal that travels faster than light through space. Light emitted from your galaxy still travels at exactly 300,000 kilometers per second through the space around you. The speed limit locally is absolute. But that light, as it travels toward us, is moving through expanding space, and the expansion of that space creates recession velocity. So even though the light is moving toward us at light speed through its local space, the space between us and the source is growing fast enough that, from our perspective, the distance isn't closing as quickly as you might expect. In extreme cases, in cases where the recession velocity exceeds light speed, light emitted toward us from those galaxies is actually losing ground. It's moving toward us at light speed, but space is expanding faster than that, carrying the source away faster than the light can cover the growing distance. This is what makes cosmic expansion the fastest phenomenon. It's not competing with light by moving through space. It's changing the space itself, creating velocities that are fundamentally different from motion. And because they're different, they're not constrained by the same limits. The universe, in other words, has found a loophole, not a violation, not a break-in of the rules, a loophole. The rules say nothing can move through space-time faster than light. The universe said, what if space-time itself expands? What if distances grow not because things are moving, but because the space between things is increasing? And the answer physics gives is, that's allowed. That's always been allowed. It's built into Einstein's equations. General relativity not only permits this, it predicts it. The universe can expand, space can stretch, and when it does, recession velocities can exceed the speed of light without paradox, without contradiction, without any violation of causality or relativity. So the fastest thing in the universe isn't a thing at all. It's a process. It's space doing what space has been doing since the Big Bang, growing, expanding, increasing the distances between objects not by moving them through space but by adding space between them. And it does this faster than anything could ever travel across it. This is the intellectual drift. The moment when seemingly rigid rules reveal their flexibility. When the question we thought we were asking, what moves fastest, turns out to have been slightly the wrong question all along. The right question was, what creates the greatest rate of separation? And the answer isn't about motion. It's about geometry. It's about the fabric of reality itself changing shape. There's a beautiful resonance here with ancient mythology. Many cultures imagined realms that were visible but unreachable, places that existed beyond the boundary of the possible. The Greeks had the islands of the blessed, paradise lands located somewhere beyond the western horizon, visible in legends but forever out of reach. The Celts had Tir na Nog, the land of eternal youth, a realm that existed alongside the mortal world but separated by something more than mere distance. These mythological realms weren't unreachable because they were far away. You couldn't reach them by building a faster ship or walking longer. They were unreachable because they existed in a fundamentally different relationship to space. The boundary between them and the mortal world wasn't a distance to be crossed, but a separation built into the nature of things. The universe works similarly. There are galaxies we can see, galaxies whose light has reached us, galaxies we can observe and measure, that are nonetheless unreachable. Not because they are too far, not because we lack fast enough spacecraft, but because the space between us and them is expanding faster than light can travel. They're receding faster than any signal could ever traverse the growing distance. They're visible, but forever beyond reach, separated from us not by space we could theoretically cross, but by the expansion of space itself. We can see their light, because that light was emitted billions of years ago when they were closer, when the expansion rate between us and them was lower, when light could still make progress. But those galaxies, as they exist now, in the present moment, we'll never see them as they are now. Their present has drifted beyond our reach, carried by expansion into a realm we can observe only in the past tense. This is what it means for the fastest thing to be expansion. It means the universe contains boundaries that no traveller can cross, not because the journey is too long, but because the destination is receding faster than the journey can proceed. It means there are galaxies that are, in a very real sense, in our past, but not in our future. We can see where they were, but we can never interact with where they are. And all of this is happening according to rules that are elegant, consistent, and perfectly physical. No paradoxes, no violations, just space doing what space does, expanding, and that expansion creating velocities that dwarf everything else we've discussed. So when we ask what's fastest, the answer depends on what we mean by the question. Fastest object moving through space, probably photons, though cosmic rays come remarkably close. Fastest massive object, hypervelocity stars, or perhaps jets from gamma-ray bursts. Fastest measurable separation velocity, the recession of distant galaxies due to cosmic expansion. And that last one, that recession velocity, is the one that wins. Not by a little. By factors of 10, 100 more. The expansion of space is so much faster than everything else that calling it the fastest thing almost seems inadequate. It's not just faster, it's in a different category entirely. The universe keeps its rules. Relativity remains unbroken. Causality is preserved. The speed of light is still the cosmic speed limit for everything that travels through space. But space itself? Space is under no such constraint. And in its expansion, gradual, inexorable, ongoing for nearly 14 billion years, it has created the fastest phenomenon we know. The fastest thing in the universe is the universe itself, growing, expanding, racing away from itself at speeds nothing within it can match. Now that we understand what's racing through the cosmos, not particles or stars, but space itself, we can explore what this means. Because faster-than-light recession velocities aren't just a curiosity, aren't just an interesting consequence of cosmic expansion. They fundamentally change what we can observe, what we can interact with, and what exists within the boundaries of the knowable. Let's start with a boundary, a horizon. Not the kind you see when you look across an ocean, but something more absolute. Something that defines not just what we can see, but what we can ever possibly see. It's called the cosmic event horizon, and it's located at roughly 16 billion light-years from us in every direction. This is the distance at which recession velocity equals the speed of light, not now, but in a more technical sense accounting for how expansion works. You can calculate it by dividing the speed of light by the Hubble constant, which gives you about 4,700 megaparsecs, or 16 billion light-years. Here's what makes this boundary special. Light emitted right now from a galaxy beyond the cosmic event horizon will never reach us. Not in 1 trillion years. Not in 100 trillion years. Never. The space between us and that galaxy is expanding faster than light can traverse it, even though the light is traveling toward us at light speed through its local space. The expansion of space itself is winning the race. The light is making progress, certainly. It's moving, it's crossing distances, but the destination is receding faster than the journey can close the gap. Think of it like running on a treadmill that's accelerating faster than you can speed up. You're running forward, you're making an effort, you're covering ground relative to the belt beneath your feet. But the belt is accelerating backward faster than you're running forward. So relative to the room around you, you're actually moving backward. You'll never reach the front of the treadmill no matter how long you run. Light from galaxies beyond the cosmic event horizon is in this situation. It's traveling toward us, but the space it's traveling through is expanding fast enough that, from our perspective, the distance isn't closing. The light is losing ground, and it will continue losing ground forever. This means those galaxies are causally disconnected from us, not just distant, not just hard to reach, fundamentally, permanently, cosmically disconnected. Nothing they do, nothing that happens to them, no signal they emit, no light they produce, none of it can ever reach us. Their present cannot affect our future. Ever. The connection is severed by the geometry of space-time itself. Now you might notice something interesting. We said earlier that galaxies 14 billion light-years away are receding at light speed, but now we're saying the cosmic event horizon is at 16 billion light-years. There's a reason for this apparent contradiction, and it has to do with the subtleties of how expansion works and how we measure distances in an expanding universe. The exact position of the event horizon depends on which definition of distance you're using and how you account for the history of expansion. The precise number matters less than the concept. There exists a boundary beyond which causal contact is impossible. But here's something that might seem even stranger. We can see galaxies beyond the cosmic event horizon. We can observe them right now. They're in our telescopes. We can measure their redshift, calculate their distance, study their properties. How is this possible if they're causally disconnected from us? The answer is time. The light we're seeing from those galaxies was emitted billions of years ago, when they were closer to us, when the recession velocity between us was lower, when light could still make progress against expansion. That light has been traveling for so long that the galaxy has since crossed the event horizon and receded into the unreachable. We're seeing its past, observing where it was, not where it is. This distinction between what we can see and what we can reach is crucial. The observable universe is defined by how far light has traveled since the Big Bang. It's a sphere centered on us with a radius of about 46.5 billion light-years. Yes, that's larger than 14 billion light-years, even though the universe is only 13.8 billion years old. This is because space has been expanding while light was travelling. A photon that's been travelling for 13.8 billion years has covered more than 13.8 billion light-years of proper distance, because the space it travelled through was expanding behind it. So the observable universe extends to about 46.5 billion light-years, but the cosmic event horizon is at about 16 billion light-years. This means that about 2/3 of the observable universe, about 2/3 of the galaxies we can see, lie beyond the event horizon. We can observe them because their light left them when they were still reachable, but they're no longer reachable now. We see their past, but their present has drifted beyond the boundary. And this boundary is moving, not in the sense of physically travelling, but in the sense that more galaxies are crossing it all the time. As the universe continues to expand, as recession velocities increase, galaxies that are currently just inside the event horizon will drift across it. Their light emitted today will be the last light from them that will ever reach us. Light they emit tomorrow will never arrive. They're slipping away, gently but irreversibly, crossing from the reachable into the unreachable. This brings us to dark energy, which is worth discussing because it makes everything more interesting and more melancholic. For decades after Hubble's discovery, cosmologists assumed the expansion of the universe would gradually slow down. Gravity pulls everything together, after all, so even though the universe was expanding, that expansion should be decelerating over time. Maybe it would eventually stop and reverse, causing a big crunch. Maybe it would continue forever, but at ever slower rates, approaching zero asymptotically. But either way, it should be slowing. In 1998, two teams of astronomers made a discovery that won them the Nobel Prize and fundamentally changed cosmology. They were studying distant supernovae, stellar explosions that can be used as standard candles to measure cosmic distances, and they found something unexpected. The universe's expansion wasn't slowing down. It was speeding up, accelerating, and it had been accelerating for several billion years. Something was pushing space apart. Something was counteracting gravity, overcoming the attractive pull of all the matter in the universe, and driving expansion to go faster and faster. Physicists call this something dark energy, which is really just a label for our ignorance. We don't know what it is. We don't know where it comes from. We can observe its effects and measure how strong it is, but we can't explain it in terms of anything more fundamental. What we do know is this: dark energy behaves like a gentle pressure inherent to space itself. The more space you have, the more dark energy there is. And because the universe is expanding, because the amount of space is increasing, the total amount of dark energy is increasing too. This creates a feedback loop. Expansion creates more space means more dark energy drives faster expansion, which creates more space, and so on. The result is acceleration, not sudden, not dramatic, but persistent and inexorable. The Hubble constant, which isn't actually constant over cosmic time despite the name, is increasing. Recession velocities are growing faster than they would if expansion were merely coasting. Galaxies are receding from us at ever-increasing rates. And this means the cosmic event horizon is, in a sense, closing in on us. Not physically moving closer, but encompassing fewer and fewer galaxies as time goes on. Galaxies that are currently reachable will cross the horizon. Galaxies we can currently see will fade from view as their light becomes too redshifted to detect. The observable universe, measured by what's actually visible, rather than what's theoretically observable, is shrinking. Let's think about the future, not the near future, the cosmic future, hundreds of billions or trillions of years from now. As dark energy continues to drive accelerating expansion, more and more galaxies will cross the cosmic event horizon. The local group, the gravitationally bound cluster containing the Milky Way, Andromeda, and about 50 smaller galaxies, will remain observable. Gravity keeps them together, prevents expansion from pulling them apart. But everything else, everything beyond our local cluster, it will gradually, inexorably, slip away. First, the most distant galaxies will fade, then galaxies in nearby clusters, then those clusters themselves. Over time, the night sky will empty. Stars will remain, our own stars in our galaxy and in Andromeda, the eventual merger product of the Milky Way and Andromeda. But the distant universe, the cosmic web of galaxies stretching across billions of light years, will disappear. Not destroyed, not gone, just receded beyond the horizon of the observable. Eventually, perhaps 100 trillion years from now, the night sky will be dark, empty, silent, astronomers living then. If there are astronomers, if there are planets and civilizations and curious beings looking up at the sky, we'll see only their local galaxy. No cosmic microwave background, redshifted into invisibility. No distant galaxies, no evidence of expansion. The universe will appear to be static, eternal, unchanging. They'll have no way to discover cosmology as we know it, no way to learn that the universe is expanding, no way to understand that they live in a vast cosmos, mostly hidden beyond an unreachable horizon. We live in a privileged time, cosmologically speaking. We can see the afterglow of the Big Bang. We can observe distant galaxies and measure the expansion. We can study the cosmic web and understand the large-scale structure of the universe. Future civilizations won't have that opportunity. They'll be cosmologically isolated, living in what appears to be an island universe, unaware of everything beyond. There's something quietly beautiful about this in a melancholic way. The universe isn't ending. It's not dying or collapsing. It's simply spreading out, giving itself more room, and in doing so, it's ensuring that distant regions drift apart, lose contact, become isolated from each other. It's a gentle fragmentation, a cosmic farewell written in redshift and recession. In Norse mythology, there's the concept of Ginnungagap, the primordial void, the great gap that existed before creation. It was the space between realms, between ice and fire, between something and nothing. And as the cosmos formed, as structure emerged from chaos, Ginnungagap remained, a reminder that separation is built into the fabric of existence. The cosmic event horizon is our Ginnungagap, a void not of emptiness, but of separation. Galaxies beyond it aren't gone, but they might as well be. They exist in their own isolated realms, forever disconnected from ours. And as expansion continues, as dark energy drives acceleration, new voids open. New gaps emerge. What was once connected becomes forever isolated, each region drifting into its own pocket of space-time, surrounded by an ever-growing expanse of unreachable cosmos. This is the consequence of having expansion as the fastest thing. It's not just that space wins the race against everything in it. It's that space creates boundaries, horizons, separations that no traveller can cross. It divides the universe into causally disconnected regions, each island drifting alone in the cosmic sea. And yet, this is also beautiful. It's the universe giving itself room, making space for complexity, for structure, for the kind of cosmic evolution that allows galaxies to form, stars to ignite, planets to coalesce, and perhaps, somewhere, life to emerge and wonder about it all. The expansion that separates us from distant galaxies is the same expansion that made those galaxies possible in the first place. So we live in a universe that's racing away from itself, where the fastest thing is also the quietest thing, the most pervasive thing, the thing that makes everything else possible while simultaneously ensuring that everything else will eventually be alone. It's strange, it's profound, and it's happening right now, everywhere, at speeds that make light itself look slow. Let's take a moment to surface, to look back at where we've been and understand how far we've travelled in our thinking about speed. We started with the Parker Solar Probe, humanity's fastest spacecraft, diving through the sun's corona at 191 kilometers per second. An extraordinary achievement of engineering, fast enough to cross continents in seconds, to reach the moon in just over an hour. By any human standard, by any terrestrial measure, almost impossibly fast. Then we looked at hypervelocity stars, those cosmic refugees flung from galactic cores by close encounters with supermassive black holes. Stars moving at 1,700 kilometers per second, nearly 9 times faster than the Parker probe. Fast enough to escape the Milky Way entirely, to spend billions of years coasting through intergalactic space, forever exiled from the galaxy that birthed them. We examined cosmic rays, particles accelerated by supernova shockwaves or magnetic chaos around black holes, racing through space at speeds where you need to add multiple nines after the decimal point before you find where they differ from light speed. So close to the cosmic speed limit that relativistic effects dominate their entire existence. Time flowing thousands of times slower for them than for us. Space compressed to a fraction of its normal size in their direction of motion. And we arrived at photons themselves, light, the reigning champion for more than a century, moving at exactly 300,000 kilometers per second. Not approximately, but precisely in all reference frames, under all circumstances. The cosmic speed limit made manifest, the universal constant that defines causality itself. These are our speed champions. This was the hierarchy we built, and it seemed complete, definitive, with light at the top as the ultimate velocity, impossible to exceed, the final answer to our question. And then we shifted our perspective. We stopped thinking about objects moving through space and started thinking about space itself. And we discovered that the fastest thing in the universe doesn't travel at all. Distant galaxies are receding from us at speeds that dwarf everything else. Not by small margins, not by factors of 2 or 3, but by enormous multiples. A galaxy 30 billion light-years away recedes at more than twice the speed of light. 50 billion light-years, more than 3 times light speed. The numbers just keep escalating. 10 times the speed of light. 20 times. 50 times. There's no upper limit, no plateau, no point where the expansion says, this is fast enough. Let's put this in perspective. The Parker Solar Probe moves at about 0.06% of light speed. The fastest hypervelocity star we know moves at about 0.5% of light speed. Cosmic rays approach but never quite reach 100%. And recession velocities from cosmic expansion. They exceed light speed by factors measured in multiples, not percentages. They're not just faster than everything else, they're in a completely different category. This is what we've learned. Speed isn't just about how fast something moves, it's about the relationship between objects and the medium they move through, or in this case, the relationship between objects and the fabric of space-time itself. When the fabric changes, when distances grow not through motion but through expansion, you get velocities that are fundamentally different from travel velocities. Recession velocities, separation rates that can exceed any speed limit you care to impose on motion. And here's the remarkable thing. None of this violates relativity. Not even slightly. Not even in some technical, loophole-exploiting way. Einstein's special relativity says that nothing can move through space-time faster than light. It doesn't say anything about space-time itself expanding. General relativity, Einstein's theory of gravity and curved space-time, not only allows for cosmic expansion, it predicts it. The equations that describe how space and time behave in the presence of matter and energy naturally lead to universes that expand or contract. Static universes are actually the unstable, unlikely case. Expansion is built into the framework. So the cosmic speed limit remains absolute. It's still there, still enforced, still impassable for anything with mass trying to move through space. Light still defines the maximum velocity for signals, for information, for cause and effect relationships. Nothing we've discussed changes that. The speed limit wasn't broken, it wasn't even bent. It was respected perfectly while the universe found a way to create faster separations through a different mechanism entirely. This is what makes the universe so elegant. The rules are strict, yes. The speed limit is absolute, yes. But the rules are also more subtle, more nuanced than they first appear. There's a difference between moving through space and having space expand around you. There's a difference between travelling from point A to point B and having the distance between A and B increase. The universe respects both distinctions and behaves accordingly. It's rather like discovering that a rule you thought was simple actually has layers. The speed limit isn't nothing goes faster than light. It's nothing moves through space-time faster than light. That one word, through, changes everything. It's precise. It's specific. And it leaves room for expansion to do what expansion does without contradiction or paradox. What we've really learned, then, isn't that the speed limit is breakable. It's that speed itself is more complicated than we intuitively understand. When we ask, what's fastest, we're really asking several different questions. Fastest through space? Fastest rate of separation? Fastest from whose perspective? And the answers depend on which question we're actually asking. For objects moving through space, photons win. For massive objects, cosmic rays and gamma-ray burst jets come closest. For velocities created by the expansion of space itself, distant galaxies receding at many times, light speed take the prize. Each answer is correct in its context. Each describes a different aspect of motion and separation and the way the universe works. There's something profound in this realization. Our intuitions about speed come from everyday experience. We live in a world where everything that's fast is moving, where velocity means motion, where going somewhere requires travelling across the intervening distance. These intuitions served our ancestors well. They help us navigate our immediate environment, predict where thrown objects will land, avoid fast-moving threats. But the universe operates at scales where these intuitions break down. At cosmic scales, space itself becomes dynamic. Distances change, not because things move, but because the fabric of reality grows. And this creates phenomena, faster-than-light recession, cosmic event horizons, causally disconnected regions, that our evolved intuitions simply weren't designed to grasp. Yet we can understand them. With patience, with careful reasoning, with mathematics and observation, we can comprehend these cosmic scale phenomena, even though they violate every intuition we have. We can measure the unmeasurable, conceptualize the inconceivable, and come away with accurate understanding of how reality actually works versus how we expect it to work. This has been humanity's great project for millennia. Ancient people asked, how fast can a message travel between realms? How quickly can gods move across the heavens? How far away are the stars? And they imagined Hermes racing between Olympus and Earth, imagined Vimana striding across creation in 3 steps, imagined bridges that shimmer between worlds. They were asking the right questions, even if their answers were mythological. They sensed that speed, distance, and the nature of space were profound mysteries worth contemplating, and in a way, they were right about some things. Hermes, the swift messenger, moves faster than mortal comprehension, and so does cosmic expansion, moving at rates we can measure but barely conceptualize. Vimana takes 3 strides that span reality, and space itself expands in ways that change the fundamental relationships between objects. The Bifrost shifts and shimmers, connecting realms, and the fabric of space-time is dynamic, growing, creating separation not through motion but through its own transformation. The universe is the ultimate messenger, not carrying information from one place to another, but creating the distances themselves, defining what from and to even mean. It's the message and the medium simultaneously, the traveller and the road, the motion and the stillness all at once. So when we ask what's fastest, we're really asking what most dramatically changes the relationship between here and there. And the answer is the universe itself, expanding, growing, stretching the fabric of reality at rates that make every form of motion look slow by comparison. The universe still makes sense. Relativity still works. The speed limit is still absolute. But the cosmos is more beautiful, more subtle, more elegantly structured than a simple list of velocities could ever capture. It follows rules that are strict yet nuanced, absolute yet allowing for phenomena that seem impossible at first glance. This is what the universe does best. It maintains rigid laws while producing outcomes that astonish us. It enforces limits while creating loopholes that aren't violations, but rather different categories of phenomena entirely. It's consistent, predictable, mathematical, and yet capable of surprises that reshape how we understand reality. We've come a long way from thinking light was simply the fastest thing. We've learned to distinguish between motion and separation, between travelling and expanding, between the speed of objects and the rate at which space grows. And in learning these distinctions, we've gained something more valuable than just facts about cosmic velocities. We've gained perspective. We've learned that the universe operates by rules more sophisticated than our intuition suggests. We've discovered that asking the right question matters as much as finding the answer. And we've understood that the cosmos, for all its strangeness, remains fundamentally knowable if we're willing to think carefully, observe patiently, and let go of assumptions that no longer serve us. The fastest thing in the universe is space itself, quietly racing away from itself at speeds nothing within it can match. And understanding that changes how we see everything else. We've travelled far tonight, from the fastest spacecraft humanity has built to hypervelocity stars fleeing their galaxies, from particles racing at near-light speed to the quiet expansion of space itself, separating distant galaxies at velocities that dwarf everything else in the cosmos. And now we come back to Earth, back to the quiet room where you're resting. The night sky above you looks calm, still, unchanging. But now you know better. Space is expanding right now, everywhere, gently stretching the fabric of reality at speeds faster than light itself. Distant galaxies are racing away, crossing horizons, slipping beyond the boundary of the reachable. The universe is in motion even though nothing moves. The universe continues as it always has, vast, dynamic, and perfectly, elegantly consistent with its own beautiful rules. If you've enjoyed this journey into cosmic speed and the nature of space itself, If these explorations help you see the night sky with new appreciation for what's really happening out there, don't forget to subscribe to the Sleepy Astronomer. There are more cosmic mysteries to explore together, more paradoxes to contemplate, more reasons to marvel at the universe we inhabit. And if this particular meditation on speed and expansion resonated with you, alike helps others discover these late-night wanderings through the cosmos. Thank you for exploring what it means to be fast in a universe where the fastest thing doesn't travel at all, for understanding that the cosmos, for all its strangeness, still makes sense. This is the Sleepy Astronomer, wishing you clear skies, peaceful dreams, and the quiet wonder of living in a universe that's racing away from itself while you rest. Good night, and sleep well as the universe expands around you, and may tomorrow find you a little more curious than today.